Hi, my name is Roman Sandoval, and I am an RF Systems Engineering Consultant and founder of Wavecast Technologies. Now this video is in review of my submission out at the Hack the Machine competition that happened very recently over this past weekend in Austin, Texas. Now Hack the Machine is sponsored by the US government, in particular the US Navy, the Office of Naval Research, DIUX, and the Department of Defense. In addition to that, Booz Allen Hamilton was there too, and they created the vessel for which we would come about hacking. That vessel is called Trudy. So, like I said before, the main objective here is to hack a maritime vessel. That vessel is Trudy and is comprised of multiple components, like radar, GPS, AIS, NEMA 2000, CAN, so on and so forth. And the objective is to attack those different components to eventually sort of control the vessel and to have that vessel maneuver in a way that's not intended. With me and my expertise in RF, I wanted to focus in hacking the RF portions, in particular GPS, AIS, and radar. It was unfortunate, however, that radar was generating and acquiring at 9 GHz, and the system that I brought in could only generate and acquire up to 6 GHz. So I focused on GPS and AIS in particular. So this is the system that I brought in. It's comprised of a PXIe chassis, and in this PXIe chassis, I have 2 vector signal transceivers. A vector signal transceiver is essentially a software-defined radio. It's comprised primarily of 2 main parts, a transmit path and a receive path. So I could generate complex IQ waveforms and also receive similar waveforms as long as it's within the instantaneous bandwidth of 40 MHz. Like I said before, I could generate between 100 MHz up to 6 GHz in each of these vector signal transceivers. Now I'm controlling these VSTs via the PXIe backplane bus, which then gets translated over to a Thunderbolt connection. That Thunderbolt connection is connected to my main host computer, which is a MacBook Pro. So most of my programming is actually happening here, and I'm executing those programs to then be executed over to these VSTs. In addition to my system, I recently purchased an AIS Class B transponder to test and verify my work. This transponder is comprised of multiple components. Here is just the chart plotter. Behind it is the receiver, and that receiver both receives AIS messages and also transmit AIS messages, and also receives GPS signals. Now I put that receiver inside this metal suitcase to create a Faraday cage so that the GPS signals that are real actually don't go to that receiver, because there's an embedded GPS receiver there. Rather, because I wanted to attack GPS and it's highly illegal to generate GPS over the air, I'm generating GPS signals, but it's through conducted wire. And that conducted wire is connected to this AIS transponder. Alright, let me go through in more detail the generation process and acquisition process of what's happening within the VSTs, and show you sort of the results that I'm seeing on my chart plotter. On my first vector signal transceiver, I'm actually generating L1 GPS signals through the RF out port. Now these signals are centered at 15.75 MHz, and they go through this cable through a set of cascaded attenuators. The total amount of attenuation is 70 dB, and the reason why I chose that amount is because I wanted to preserve the dynamic range of my vector signal transceiver, at least on the transmit path, and also significantly attenuate that signal such that it reflects what the typical power level would be when a GPS signal hits a GPS receiver. Now it's important to note that GPS signals are very close to the noise floor, and that's why I chose 70 dB of attenuation. In addition to that, I've added a DC block to compensate for the DC biases on the receiver, and then I've obviously connected this cable over to the GPS receiver of the AIS transponder. So what you'll notice is that on the chart plotter of the AIS transponder, the satellites are actually being registered. Now, I'm generating in real time the updated clock information, the updated ephemeris and almanac information, and also updating the coordinate system, the trajectory and direction of the vessel. So now you'll notice is that the vessel is actually moving when in fact the vessel is stationary on my desk. The second approach to hacking the machine was to create fake AIS messages. And instead of going through the entire AIS protocol stack of modulating and demodulating these Gaussian minimum shift keying messages, I needed a faster way and a faster approach. And so I've decided to do a record and playback system where I would connect my own AIS transponder over to my second vector signal transceiver to the RF in and collect all of the IQ data centered at 161 megahertz such that I could repeat those same complex waveforms on my vector signal transceiver over the air. And so I would save the waveforms in my solid state disk and then sort of repeat those waveforms on my RF out of my vector signal transceiver to try to spoof the AIS system of Trudy. Now you'll notice that this RF out is then connected to the antenna on the back of my PXIe platform. So this is generated over the air. So that completes the review of my system. The next few photos are of Trudy, and you'll notice that there are indeed a lot of various components on Trudy itself, including the GPS receiver and the AIS transponder. Thanks again for watching, and have a good day.